We will look at an important factor which is called the eddy covariance in measurements of CO2. So we have been talking about CO2 increases, but how do we measure that? So eddy covariance is the method by which it is actually measured. So an eddy is a circular motion of air created by temperature fluctuations. A covariance describes how two things change together. So that is what eddy, that means the temperature fluctuation is correlated with the wind, how it is changing. That is what is the measurement. So at night without the sun, the air is cool and relatively stable. With the rising of the sun, the earth and air temperature begin to increase. So this constant night and day fluctuation in the temperature creates the wind and the eddies of the air, which we can measure. That is change in the concentration of the gas and the wind direction we can actually measure. So this is also called as turbulent flux method because there is a change in the wind directions or wind mixing. So it is used to measure the canopy atmosphere gas exchange or the flux or soil and atmosphere gas flux, or it can also be used to measure the benthic, that is sediment water gas exchange or fluxes from water and wetland surfaces. So there are various places we can actually measure this difference. One may be between the canopy and atmosphere, that is one region. Another one is soil or land and atmosphere. The next one is benthic or the sediment and water gas exchange, or the fluxes from water and wetland surfaces. So these are all the various ways by which we can actually measure the eddy covariance. This is usually used as a land-based application. Moving vehicles, airborne and shipborne installations are increasingly emerging in the flux network. So currently people study using the land-based applications. So we will look at how it had developed over a period of time. So in 1920s, the early concepts were developed. So researchers were studying turbulence and atmospheric boundary layers, laid the groundwork for eddy covariance. This led to the emerging concepts related to turbulent flow dynamics. So this is the starting point. Then initial applications, the term eddy covariance originated from measuring momentum fluxes. Scientists like M.S. Smith, who was exploring the turbulent flow dynamics and atmospheric implications, have coined this particular name. And then in 1970s, the technologies were developed. That means advances in the fast response sensors helped us practical eddy covariance applications, and this helped us measure the gas exchange, especially carbon dioxide and water vapor fluxes. Then in 1980s, the use was broadened. And then in 1990s, standardization of the networks started happening. And in 2000, the global application started implemented. And in 2010, the remote sensing was integrated into the measurement. And currently in 2020, we are using advanced precision and scales to measure the eddy covariance. So here is a pictorial diagram of how the eddy covariance actually happens. So the wind direction is in this direction, from left to right it is moving on, but the arrows whatever you see are the one where the wind is actually flowing. One is the carbon dioxide coming down due to photosynthesis, another one is carbon dioxide going up due to the ecosystem respiration. So both the things happen simultaneously. So that is the reason there is a lot of flux that is happening, and also we have a ecosystem respiration, that is soil and plant also respire. So the carbon dioxide, so the flux towers are set up like this just above the plant height, and then the eddy covariance tower measures the flux, how the wind direction is changing, and with respect to wind direction, how much CO2 or moisture is present in that particular space or the atmosphere that is being measured. So basically the eddy measurement is done in the internal sublayer, and these are free from obstructions, because otherwise the wind, if it is blocked, then we may not be doing the proper measurement. So that's the reason it is always kept above any obstructions. How much area it can cover basically, which is called as the zone of interest. So vertical and horizontal distance is the main thing, and homogeneity of the spatial area and canopy is another important factor we have to consider. Otherwise the variations are going to be extremely difficult to understand. How much height of the sensor should be kept, that is called as a zone of influence. So lower the height will have closer fetch area and the higher height will have longer fetch area. So that's the only thing. If we kept it very close to the surface, just above the plant's height, then we will be having the wind dynamics is very low in this direction. But if we keep it at a very high level, then the wind flow or the directions or the wind dynamics is going to be quite different. So depending on how do we want to measure, we can actually use or change the height of the eddy flux tower. What is the limitation? It's very easy to study under dry condition compared to wet condition. When there is rain or precipitation, it's very difficult to measure, because not only the wind keeps changing, and even the water droplets which are present make it very difficult to measure the flux, how it is happening, because the temperature also lowers. In the urban areas, measurements has to be carried out at the top of the building or telecommunication towers, because there only the wind dynamics will be much more easy to understand. We need to pay special attention to flow distortion areas near the measurement points, because if we keep it just above any building height, and if there is a blockage from the nearby building, then the wind direction or the wind dynamics is going to be affected, which will have a far-reaching effect on our measurements. So that's the reason we have to make sure whatever may be the height we are keeping, it should have no blockage. And it should not be near any air pollution sources, because air pollution means currently what we can talk about is carbon dioxide pollution. So that means those areas, if we keep it, then we will be having lots of carbon dioxide in the air. So that means the measured eddy covariance may not be the actual one that is happening, because that area is highly concentrated, whereas if we move away from the polluted sites, then the carbon dioxide concentration may be less. So that means there is going to be a lot of disparity in our understanding and measurement. So what are the components of the eddy covariance flux tower? We have the flux towers. This flux tower basically measures the net ecosystem exchange of carbon dioxide. There is a anemometer, which is many times people use sonic, which measures a 2D or 3D wind speed and the direction. So this is one of the important thing. And then the infrared gas analyzers measure the gas concentration of water, methane and moisture in the air. Air temperature and relative humidity are measured separately, and battery or solar power is used to supply power for entire system or the unit. The data are collected simultaneously thousands of times per minute, and by combining the field measurement and satellite data with machine learning methods, we can map greenhouse gas fluxes in the Arctic region. So what are the components of wind? We have been talking about wind direction, wind dynamics. So let us look at what are the different components of the wind. The first one is U component. This represents the east-west, that is horizontal wind speed. A positive value indicates wind blowing from west to east, that is the easterly wind, while the negative value indicates wind blowing from east to west, westerly. So that means the sign does not mean it is more than 0 or less than 0. It is only the direction, especially in the U component. And when we look at the V component, this represents the north-south, that is the horizontal wind speed. So here a positive value indicates that the wind is blowing from south to north, that is northerly wind. And if it is a negative value, that means it is a southerly wind. And the W component, this represents the vertical wind speed. A positive value indicates upward motion, that is ascending air, while a negative value indicates a downward motion, descending air. So how do we calculate U, V, W from wind speed and direction? The wind speed V is equal to the speed of the wind, typically measured in meters per second or knots. The wind direction theta is the direction from which the wind is coming. It is measured in degrees from true north 0 degree. To calculate U and V, we can use the formula U is equal to minus V dot sine theta and V is equal to minus V dot cos theta. So here are the eddy covariance measurements. The complete calculations are given. The key formulas involved in the eddy covariance measurements focus on calculating the fluxes based on turbulent wind measurements and concentration changes. So the primary formula for the flux calculation is given here. The F, capital F, is the flux of the gas, especially CO2. Here it is usually expressed in micromoles per meter squared per second. And omega W prime is the vertical wind speed fluctuation, that is deviation from the mean. That is, then C prime is the concentration of fluctuations of the gas, that is deviation from the mean. Here, this indicates that the average over a specified time period or condition. So based on that, the bar is actually used to say it is an average. The covariance calculation is given with the formula here. N is the number of samples, that is how many times we measure it, and W1 is the vertical wind speed of the ith measurement, and Ci is the concentration of the gas of the ith measurement. Omega bar is the mean vertical wind speed, C bar is the mean concentration of the gas. By using this formula, we can calculate the covariance. And then we have to actually apply some correction factors. This is the density correction factor has to be applied. So to account for the changes in the air density due to temperature and pressure, especially in the measurement gases of CO2. So we apply this particular formula FD, that is the density correlated flux equal to obtained flux divided by the rho bar, which is the mean air density. So what is the stability conditions? To adjust the atmospheric stability, we use stability parameters such as the Abuglu length L and the friction velocity Ux. So total flux integration is calculated using this formula, and net ecosystem exchange can be calculated from the given formula. NE is equal to F of CO2 minus GPP plus R. GPP is gross primary production, R is the ecosystem respiration. So how much CO2 is being consumed by the plants and how much the system respirates. So these two are actually used to find out the net ecosystem exchange values. So here is the diagram which explains the various layers in the eddy covariance measurement calculation. The surface or the soil layer is considered as the zero level, and there are plants and other things which are there. So basically this is called as the height of roughness element. So the roughness of sublayer is generally considered as 1.5 to 2 height of the roughness element. Roughness element means any rock or plant or anything that is just staying above the surface, which makes it like it is a non-uniform surface. So anything that is not non-uniform, they are considered as roughness. And if we consider 2 to 5 height of roughness element, if we consider, that is basically may include a canopy layer also. And the eddy covariance layer is basically from 1.5 to 2 height to 100 to 150 meters. So this is the area, or this is the region where people generally measure the eddy covariance. So measurement is basically based on the height, and the turbulent fluxes of the gases are measured. We use vertical wind component, concentration of fluctuations, and all those parameters given here are used. And anything above 150 meter to 1000 meter is basically called as a mixed layer, and above that is called the atmosphere. So the eddy covariance layer is this area which is roughly 2 height of the roughness element to 150 meters. FluxNest is basically a global network of micrometeorologist tower sites that use eddy covariance method to measure the exchange of carbon dioxide, water vapor and energy between the biosphere and the atmosphere. It is hosted by the Lawrence Berkeley National Laboratory, and it is available for download by anybody. There are also regional networks are there. So using this, we can actually measure, we can easily understand how the CO2 is getting exchanged.